So a foundational concept in number theory is the idea of divisibility. Let a and b be integers. We say that a is divisible by b, or that b divides a, if there exists an integer k such that a is b times k. And we write it this way. If no such integer exists, we write b does not divide a. For example, we might try to prove or disprove that 12 divides 36. So remember, definitions are the whole of mathematics, all else is commentary. So if possible, we want to write 36 as 12 times something. Since 36 is 12 times 3, then we can say that 12 divides 36. And a useful strategy, what else does this tell you? Since multiplication is commutative, then we know that 36 is also 3 times 12, so we also know that 3 divides 36. Or let's try to prove or disprove that 4 divides 10. Now, since 8 is 4 times 2, and 12 is 4 times 3, and there's no integer between 2 and 3, then there's no integer where 10 is equal to 4 times k. So 4 does not divide 10. Now, note the claim that there is no integer where 10 equals 4 times k requires on the continuity of multiplication by 4. We should prove this, but that's another course. Let's prove something important, that 1 divides n for all integers n. Now, since n equals 1 times n, 1 divides n. And also note, again, since multiplication is commutative, n is n times 1, so n divides n for all integers. And this actually is a proof, and so we can say, as a theorem, for all integers, 1 divides n, and n divides n. A useful strategy in mathematics, and life, once you have a tool, find problems it can solve. In this case, our tool is the idea that b divides a. Well, suppose we know that b divides a. Is there anything else we know? So remember, definitions are the whole of mathematics. All else is commentary. Suppose b divides a. Then from our definition, we know that a is b times k. Now, in number theory, it's useful to keep in mind we should always multiply or add, and multiplication is easier. Consider any integer p. If we multiply by p, we get pa equals p bk, which we can rewrite. And since pk is also an integer, we get the corollary. If b divides a, then b divides pa for any integer p. Now, since one goal for this course is to develop your thinking habits as a mathematician, another useful thing to do is to consider the converse. So we just proved that if b divides a, then b divides pa. The converse would be that if b divides pa, then b divides a. But does it? Remember, if you don't find your mistakes, someone else will. And in this case, we can find a counterexample. We see that 4 divides 8 times 3, but 4 does not divide 3. But again, since part of the goal is to try and develop your intuition as a mathematician, another thing that's useful to keep in mind is that retreat is always an option. While 4 doesn't divide 3, we note that 4 does divide 8. So maybe it's the case that if b divides a product, then b will divide one of the factors. Now, rather than try and figure out something that divides, let's remember that any integer divides itself, so 4 divides 4, but 4 itself is 2 times 2, and 4 doesn't divide 2. Well, again, retreat is always an option. Is there any case where this is true? What if 2 divides a product? So if 2 doesn't divide p, then p must be odd. And if 2 doesn't divide A, then A must be odd as well. But then PA would be the product of odd numbers and be odd, in which case 2 doesn't divide the product. This means there's something different about 2. And as we'll see, 2 is a very odd number. So again, a useful strategy in mathematics and in life, don't stop with just one corollary. So we found that if PA equals PBK, then PA is also PB times K. And by our definition, this says that if P divides A, then PB divides PA for any integer P. Now, whether or not these corollaries and these other results are useful is almost beside the point. We might use them, we might not, but the important goal is to create them and, more importantly, to get into the habit of drawing the corollaries, considering counterexamples, and considering how we might retreat to produce a usable result.